Assalamu alaikum. Today we are presenting our MATLAB project DC motor speed control system, which is built around one of the most widely used control algorithms in whole engineering, the PID controller. I Adib Muhammad and my friend Albi Muhammad will help you to walk through every aspect of our project. So what did we actually build? Imagine you have a DC motor and you want to control its speed at a certain RPM. What happens if a mid-load is introduced or any disturbance hit? Does it overwhelm? Does it recover? Or does it fail? If it recovers, how fast does it recover? Our project will answer all of your questions. Our project is built around three MATLAB files. The first is simulate motor, which is the real backbone of our model and calculates the differential equations. Then there comes the motor logic, which is the analytical brain which calculates the performance matrices. And then comes the motor GUI, which is the user friendly interface to walk the user through everything.
Assalamu alaikum everyone. I am Albi Mahamud, a student of board Tripoli department. Today I am going to explain the function simulate motor, which is a fundamental function of our MATLAB project named DC motor speed control system using PID controller. But before getting started, we need to know about some important equation of DC motors, which are these three equations. First equation is for armature voltage. Here Kp, Ki and Kd is the three gain value of PID controller and E is the error function. And the next is armature current. Here Bi is the armature voltage from the previous equation, and I is the old armature current, and R is the armature resistance, and Kv is the back EMF constant, omega is the speed, and L is the armature inductance. And third equation is the mechanical dynamics equation of DC motor, which where omega is the speed of the DC motor and Kt is the torque constant. And now come to the function, the code. Here first we are taking the input. Here params and PID is a stack, where the params contain R, L, J, KT and KB. Here J is the moment of inertia and reference speed, load torque and simulation time and the time interval. First we are making the time vector, then we take in the speed vector and current vector. First we initialize these two with zeros and take in the previous error 0 and the integral is 0, and we are assuming that the load is added at the half of the simulation time, and then we are starting our calculation. First we are calculating the error, which is reference speed minus omega, and here we are doing the integration by Euler method and calculating the derivative. And this line is the first equation I have explained before, which is BA armature voltage equals to Kp into error plus Ki into integration of error and plus Kd into derivative. Here the integral and the derivative is calculated this in these two line. And next is the armature current. We are using the exactly same equation I explained early. Here is this equation, and this line is doing the integration. Here first we have calculated the di, then we integrate di to get the I, which is I equals to integration of di. And then the load torque, we check in the load torque is added or not by this line. Is if the load is added, the load torque value will get stored here, and if not, the load torque will be the value will store here is 0. And then we are calculating the speed using the mechanical dynamic equation of DC motor. First, again the same method we followed here. First we have calculated d omega, then we indicate using Euler method. Means here omega equals to integration of d omega. First we have calculated d omega, then we have done the integration, and in the last we are storing the this error in the previous error, and then again calculating the errors. Okay, thank you.
Now I am going to explain the motor GUI. First you have the launch button. If you launch, in the first input window you have to give the hardware parameter like armature resistance, inductance and back EMF. Then the second window you have to give the gains, PID gains, proportional derivative gains. In the third window you have to give your references, target speed, load torque, etc. Then if you click, the output will be shown and you will have the option to see the plot. Then to explain the motor logic, we calculated the steady state error, rise time, setting time and overshoot. Steady state error compares your given reference to the actual value in the output. Rise time uses the standard 10% to 90% criteria, which means that the time it takes to for the motor to get to 90% of its speed. Setting time uses the 2% criteria, the identifying the exact moment the speed stays within 2% of the target without leaving again. And then there is the overshoot. It calculates the percentage by which the motor exceeds its target speed before stabilizing. Now I'll show you how the application actually works. If you run the GUI file, it will show you the first window, which is the launch simulation. If you launch the simulation, you have the hardware input. First I will show the default values, then I will show you after changing the values. Next is the PID tuning, proportional integral derivative gains. Then there is the reference values, reference speed, reference torque, and simulation type. If you run the analysis, it will give you the four analytical parameters: rise time, setting time, steady state error, and overshoot. You have two plot option. If you click them, it will show you two plots: the speed plot and the error plot. This is the speed plot and this is the error plot. If you want to change the matrix, you can do that also. This time I'll show you the changing some parameters. Let's say the resistance is 5 ohm, proportional gain let's say 2. You can change everything. I am changing onto parameters, and reference speed I like to 90 rpm. If you run the analysis, it will show the four performance matrix, and there is two plots: the speed plot and the error plot. There is the speed plot, here is your error plot. This is all for my demonstration. Thank you for being with us. Thank you.